I studied electrical engineering and now I'm doing a PhD in printing of organic devices. For those not so familiar with it, I work with OFETs, which are organic field effect transistors. Organic field effect transistor is a part of circuit which is very basic, very important, and it's in a lot of your electronics. And it works more or less like a water tap that has 3 entrances, 3 valves. Your water tap here, your entrance here, another water tap. So you have 2 water taps. When you want your water to flow here, if you open this first water tap, this water will flow if you get to open this water tap. So if you open it a little bit, your water goes in just a little bit. If you open all of it, all the water comes out. What a field effect transistor does is basically the same, but instead of using tap, you use voltage entrances, and instead of water, you get charges to pass through here. So like a water tap, for you to get this channel and get the water to go through it, you usually want pipes that look like a very smooth channel. But if you want the water to go through, you want it to go smoothly through the water pipes. If you have a water pipe that looks something like this, you want to take a shower and it's going to take 10 minutes for the water to come through you, right? You don't want that. What I do in my project is take this channel, which is our active layer, and try to optimize it using printing. In our channel is what we call the active layer, where all our charges go through. And it's solution process, which is a new recent method for around 20 years. My job is to make this better. When you want to grow this channel, you want it to grow in organized scales. So you make this channel out of little molecules or polymers. So you have your little molecules here, and you want them to pack nicely. So you want them to be very ordered. You want them to pack one in front of the other. When they pack like this very nicely, they create this very ordered structure. If your molecules are all over the place, all like this, your charge transfer will be very difficult. And like your water, it's gonna take a long time to come through. You open the pipe, you're still waiting, and it's like you have electronics that are really slow. And in order to optimize that, I use an existing printing process. I will give you a brief explanation of the printing process. For example, here is your substrate. This is where you want to put your active layer, your little molecules forming a crystal. How do you deposit it that it's nice and smooth? We have this blade, which is like shearing your material onto a substrate like butter, and it forms a really nice film. And this film is what we have as the active layer, the channel for the pipe channel, where the water would come through. With this, we get to form really nice thin films, and depending on how good we control this film, temperature, pressure, concentration, can get very nice films or very crappy films. It's part of the job to control this. So here is where the crystallization occurs, where the film channel forms. So once it starts drying, it forms a little channel here, your very nice organized blocks. Then when you continue shearing, it forms another little layer here. And this is your really nice pipe structure. But at some point, for it to be this nice, it takes a very long time. For example, it takes years. But if you want something to be commercialized, you can't wait that long to have that amount of material. The challenge is to make these very nicely structured as fast as possible and as cheap as possible. So when we are shearing our materials, for example, we come with our blade like this. And then we start growing our crisp. And at some point, because it's not slow and it doesn't take years to grow, it starts going all over the place. Here, it goes here, it goes here. And the same way as water pipes, if you would have water going through here, every time it has to deviate from a place or go from part to part, it gets slower. We want to get rid of these connections here, these defects. But this is something that, as the faster you shear, the worse it looks. So we want to come around this by introducing an extra artifact in our shearing process. At the moment, there's no way to just using regular printing make single crystals. And single crystals is this very smooth channel, perfect channel where you can get the maximum speed out of it. What we try to do is apply a force here. So we have our blade here, our material, and when you get like a bottle of water and you shake it with something inside, it all mixes up and dissolves if there's a type of precipitate inside. So the same way, these little precipitates or pieces of where solution have too much material or super saturated that create these little boundaries, crystals that go everywhere, we want to mix them with our shearing, with our printing mechanism in order to make them more continuous. So instead of having here at where you're making your material, points where they start crystallizing everywhere, you want to have a smoother film and more organized. But how do we do that? Does anyone have suggestions? Okay. Maybe.
He was against.
No, I mean, actually, if you have a better idea. It's still bad. It's still not. What we do in order to shape this blade while it's printing is put a vibrational mechanism here. So it's a tiny crystal that when you apply voltages, it expands and contracts, and by, for example, applying an alternate voltage, we can get it to move like this, which moves our blade like this. And then our liquid is supposed to mix and form a more continuous layer. So this is my project at the moment. So far what we wanted it to do would to be improved crystallization, to make these very nice smooth films and channels that would be single crystal. And some things that I have seen, these are some initial results, were for different materials, different concentrations. They work a bit different from what we expected. Sometimes compresses the material, sometimes if it's an open film it can close the film, but this is a lot of handiwork. The shearing process, the crystallization process, is a little bit tricky. Various tiny factors make the output look quite different, so it's difficult to evaluate what is done by our vibration mechanism and what is not done by it. One difficulty is finding a setup where we can see a real improvement. For example, if we have a small variation in an experiment from sample to sample and from batch to batch, it's difficult to tell what is the effect of the external mechanism. So if it's not completely uniform the whole time, you can't tell it apart. And once you tested all these frequencies, which we can test from now from 0 to 100 kilohertz of vibration, sometimes repeatability is a bit tricky because very tiny factors influence in the production. Sometimes they get masked, sometimes the effect gets masked by these things that we think are a variation, or sometimes things that we think are an effect of our new mechanism are actually just a variation. It's a bit of a control problem at the moment.
What is the size that you are handling there of your device and the printing?
One single device has 100 micrometer channeling, but the whole sample, it depends on how big you would like to make your blade and your substrate. At the moment, we can make samples, you can do up to 4 centimeters by 2, so 8 square centimeters, in a few seconds.
But what's the thickness of your layer?
The very good ones are around 15 to 20 nanometers. The thinnest that I have made were 7 nanometers.
What you can change.
So if we have the shearing setup here, we have the substrate, and this we can control the temperature. So the higher the temperature, the faster you can evaporate, and probably the thicker it will be. Then you can pick your solvent, and depending on the boiling point, it will be thicker or thinner depending on your temperature. And then you have the speed. The speed is really easy to control, the temperature, annoying. The concentration, or the more concentrated, the thicker. So you have to reach balance between all of them. So at some point, the better films, not so thin, not so thick, from both sides they become bad, being thick or too thin. Then you have to find like an optimal point for each setup. Student work.
You're making molecular crystals, right? So basically, you condense molecules, but how are they connected?
Using these small molecules, they are prone to grow edge-on. So we have benzene rings here. With a surface treatment, we can get them to grow edge-on. So they grow like this. I mean, depending, they grow in different...
But in the end, they are not separated anymore.
No, they're connected. Sometimes you get a few millimeters grain in this direction, and then you get a boundary here. But these films are all interconnected. Because they're very thin, they don't crack. I mean, if you go thicker, you can get these cracks and disjointed films, but you can control with these parameters that they're very continuous. We have the packing like this, and they have these pipe-wide stackings, and the charge transfer happens like from less strong bonds. They get delocalized and can flow through the packings of molecules. This treatment that we do, it is in order to guarantee wettability, that it adheres to our substrate, and that it packs in this way. So even if we would have very edge-on structures this way, they would grow edge-on the substrate in the other dimensions. So the problem is not really being an edge-on. That is also for very thin films, they manage to have it already, at least good control of this.
Why is organic transistors better than the normal transistors? So what is the use case? Why is it so interesting? What could it offer us?
At the moment, they are not better. They have a potential to have different applications. If you would want wearables, for example, for skin, or if you have a prosthesis and you want to put sensors in it, or a lot of medical applications, for example, band-aids where you can sense things, bendable screens, if you would like to put it in somewhere soft or somewhere transparent or somewhere where it needs to be humid, there are some materials and devices that have shown to be resistant to water and humidity, or even good for sensing water and humidity. So if you would like to have something inside your body someday, you could use these organic transistors. So they're not better in performance at the moment, but they have potential for different applications than
In which atmosphere do you process in a clean room or?
No. This is another advantage from the organic materials, is that they try to make them a bit more low cost. So we try to use materials that are air stable, which doesn't happen all the time, and you find out halfway through. So some of them are, or they last a few, for example, surface treatment lasts a few hours, so you cover them before they go bad. Sometimes the semiconductor is very stable for several days, or sometimes it's stable if you do a certain treatment to it, or it's stable if you keep it in a glove box. But all the processing, it happens in air. Sometimes the measurements are better if you do it under nitrogen, but one of the important things of it is that it's done.
So you doesn't have any influence of dust in there or something like that?
Yeah, it has. So that's something also that environmentally, for example, humidity, temperature, outside, sometimes we don't know how the saturation at the front of the printing is. Environmental factors at the moment change a little bit of our experiment. So that's also something that we try to work around, but it's not so much under control.
Thanks again. And now we just talk.